Hello. Hello. Hello, Michelle. Hello, Mohammed. Hello, Luke. Ah, good. Oh, okay. Going for the awesome. Hold on. Good morning, Nadine. Good morning, Mark. Good chat time. Good morning, Mo for the double. Michelle for the double. Mark for the double. Or for the well, yeah, anyway. Luke, good morning. Okay. Wait, small class today? Huh, interesting. Okay. We're all exhausted. Okay. Let me so still more exam. I think I mentioned this Monday. I've done more exams. I've not done them all yet. I'm not promising an exact moment of return, but they are in progress and they're looking good, and you will get them at a reasonable time. Again, my goal is the end of this week. I don't want to set myself up for, but anyway, but they're happening and they're good. So I'm going to go on with physics now. I believe. Very small class, huh? Okay. I believe, um, tell tell me if I'm wrong, but Monday in class, we finished, we actually got answers correct to that homework that was due Monday. Yes, thank you, Nadine. Perfect. Okay. Okay. And then you went into the lab. I saw you in the lab. That was great. So quick thing about the lab, I guess my impression in the lab is that and I know it's a different, we already discussed, it's like it's a parallel track to what we're doing in the lecture, but it will hook up, at some point. You'll see the connection, the direct connection between the underlying theory that we're doing here versus the practical consequences that you're seeing there in the lab. Um, did I start a little bit early accidentally? I'm sorry. Okay. Anyway. All right. So hang on. All right. Good morning, Jalila, and good morning, Melanie, and good morning, Lunar. Okay. Awesome. Awesome. All right. I will just All right, we were just saying, so so my impression so again, to reinforce that, like, what you're doing in the lab is obviously, in the same larger topic as what we're doing in the lecture, but it's not it's not clear how to directly apply the concepts of the lecture yet to what you're doing in the lab. I totally understand that. I mean, other than that, like, positives attract negatives and positives repel other positives. I mean, that's fundamentally what's happening in a circuit. But um, so you're okay. Chat. Oh, oh no, okay, okay, thank you. I appreciate it. All right, no, I totally appreciate it. I actually thought it was no, thank you. Direct chat person. There's only one of you. I get it. Thank you. Oh, and Deshen, good morning, and Joshua, good morning, and Lunar, good morning. And we said, okay. So anyway, all right. So I want to get back to the electrostatic theory stuff that we're doing in the lecture. Again, saying to those of you who just walked in, saying that understanding that right now it's a little difficult to directly apply the lecture material to what you're doing in lab. Totally understood. In lab, it's a bunch of concepts that you're sort of figuring out as you go and inducing from success or failure with I shouldn't say failure, success or challenge with light bulbs and so forth. But the two, you will see how the two interconnect in a couple of weeks. So quickly, so I believe next week in the lab you'll be continuing not only that similar type of activity, but in fact specifically, I think that same document, if I'm not mistaken. Um, um, like, I don't think you finished everything 2 days ago. Is that correct? Like, there's still stuff to do in yes, thank you, Nadine. Great. And thank you, somebody else who I can't tell, but yes, thank you. Okay. All right. So all right, but I'm just gonna keep going with the lecture material here. So I will switch the view. Um, what I want to say, well, here, okay. Okay, here's where the material's going now. Oh, cool. Okay. And I will switch the view in a moment just to let once I really start drawing pictures. Here's the deal. That homework that you did, that we went over yesterday, that was a rather thick computation. Like, I'm really glad we all did it. I think we all learned a lot. Hope. But it's not something any of us really want to do many, many times in our life. Add all those vector components, right? And let me remind you of what it was that we were doing or what result we were getting. We were saying if there's a dot of charge over here and another dot of charge over there, what's the collective impact of those two dots? What's the combined effect of those two dots on a location over here, right? In technical terms, we were asking what is the electrostatic field at a location due to the superposed effects, the superposition of two discrete point sources somewhere over there. We were figuring out the field due to two point sources, and it was a lot of math. Now, and again, let me remind you that the field is something that exists at a location due to charges at other locations. In fact, let me go a step further and say the idea of the field is that if there is stuff happening over here, if there's stuff existing, if there's mass, or in this case, charge existing over here, then the information of that charge, like the size of it and the particular location of it, are known to space anywhere and everywhere else. The idea of the field over here is the information, the sizes and locations of whatever kinds of charge is anywhere and everywhere else, right? That's the idea of the field. So we just did this huge calculation to figure out the field at a spot due to two point sources. As as I might have mentioned Monday, of course, in any realistic situation in the lab or in the universe, at any given point in space, the field is the result of a lot more than just two dots. There's tons of dots of charge everywhere. I mean, there's air. Air has nitrogen, and other stuff, and oxygen, etc. Each nitrogen atom and each oxygen atom has a whole bunch of protons and electrons. So, and that's just the air itself, right? So any point in space you are, you you are experiencing a bunch of vectors adding together from all the stuff that's around you. The closer stuff being more relevant than the farther stuff. So there's got to be a way to manage this reality, to make these computations. We don't want to sit and add vector components like all day long. We believe that is what's happening. Again, let me say, like, why you did that whole exercise yesterday is that's an example of what we think is going on in nature. That when there's a vector from over here and a vector from over here, they add together and create a resulting field information over here. But we can't go through that all the time for all the points that exist in the world. So there's got to be some. So thinking of the field as a bunch of vectors is correct. And when I'm trying to picture field, in my mind, in my life, I continue often to think of a bunch of vectors everywhere in space. But it is just a way of thinking, right? I mean, no one's arguing that arrows literally exist in space. We're arguing that information exists in space, and and one easy way for us to picture it and manage it is with arrows. So what I'm getting at is hopefully there's other ways to picture and compute the field that will allow us to sort of step up the food chain and start picturing not only many, many more dots of charge at once, but maybe to start picturing bunches of dots that are so close together that they're in fact like infinitely close together, bunches of dots that are continuous in their arrangement, right? In other words, what I'm trying to move here, and I'm going to turn the page, and I'm going to move the board view in a second. But where we're trying to head now is there a way that we can picture not just dot, 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 not just pixel, 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 but like smear of charge and what impact that has on the world. Instead of picturing a bunch of dots near each other, could we start doing the physics of, say, a wire, like a line of charge, like not dot, 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 but like line of charge as you're sort of experiencing it, oh, in lab, right? Like in the wires, you're experiencing continuous lines of charge where the dots inside are so close together, you don't see the gaps between the dots. You don't see or experience the gaps between electrons that are moving around in those wires in the lab. So how do we deal with that? How do we deal with continuous charge distributions, shapes such as lines, spheres, planes? That's where our ship is heading now. Okay. So the first, so we're going to move. I'm going to turn the page as I keep saying. We're going to move in our mind from the representation of vector field diagrams to something called field line diagrams. Different way of, same reality, same information, magnitudes, directions, but we're going to start like picturing it a slightly different way and therefore doing the math a slightly different way so that we can handle bigger picture realities. Okay, so I'm going to turn, and then I'm going to turn the view of the screen. So this, what I'm going to draw first, is a reminder of something we already believe. I'm saying this is a reminder because it's an old it's a concept that you know, but I've never literally drawn this before. Okay, so you do want to draw this. And you definitely, I'm making it look like sort of. I'm making it look like it's obvious, but it might not be. Like you feel free to ask questions. Is what I'm saying. Okay, and I'm going to change the view. Oh, who? Okay, the meanings mean transcript. Hold on, hold on. Okay. Okay, so this picture that I just drew, what is that? Like, okay, so this is this is thinking of fields as vectors, right? And I'm saying if you put a proton in the world, in the lab, like if you just have a proton, what our belief about fields now, our belief is that the proton, just by existing, or the positive Q, some amount of protons jammed together, some into a dot, somewhere in the lab. What we're saying is now in all of space, space is aware that that proton is there. Like that's the concept of the field, is that the proton starts pushing everywhere in space, pushing like a tractor beam or something. Like it's starting to push such that now there's nothing that it's pushing on, but it's pushing like ready to go, so that if a test charge of +1 coulomb came anywhere in space, it would be pushed by this field that's there, pushing, ready to go. And the way we picture that is that means at any given moment of space, excuse me, that didn't make any sense. At any given location of space, there is a vector sitting there at that location, a vector created by plus Q. And it's a vector that has a particular magnitude in a particular direction. And these vectors that I just drew here are a representative sample of the pattern of vectors that we believe exists everywhere in space due to plus q, right? I'm saying there's vectors everywhere. You name a location, there's a vector there. Technically, the field is a vector valued function. You input the location, and Mother Nature outputs a vector at that location. Well, I've drawn some of them, just enough kind of to show you the pattern of those vectors. And it is a very specific pattern. If we had one dot of charge, of positive charge, what I'm trying to convey with this pattern, this picture, is that no matter where you are in space, you're going to be sitting at a vector that is necessarily pointing away from the point source, like along the line, like each one of those vectors, if you really understand what I've been trying to say about vector, each one of those vectors is like a stretched out version sitting on a little r hat. It's sitting on the imaginary line that would connect plus q to whatever point you're looking at, like point whatever point you're looking at. The as in the homework you just did, the point you're looking at was like the origin, right? And I generally call that point the location of interest. ChatGPT and like the web and stuff generally calls it the field point, whatever, or P, whatever you call it. If you imagine a little r hat vector directed from plus q to that point, then the field arrow points along the direction of the r hat vector, along the radial line emanating from plus q and going to that location. So there's a vector sitting anywhere, pointing like out like that. But then notice furthermore that the vectors their sizes. I didn't draw it perfectly to scale, but what I'm trying to get across is as you get farther and farther away, the vectors get shorter and shorter by like a certain amount. Because the field, because this whole thing is a pictorial, this is supposed to be a pictorial representation of our belief in this. That the bigger the Q, the bigger the arrows, but the bigger the R in the denominator squared, the smaller the arrows, right? The farther away you are, the weaker the field. And so, okay, so I'm over talking it. So you see, the arrows always, so anywhere you are, you're on an arrow that's pointing away from Q with a certain length that gets shorter and shorter as you get farther and farther away. Similarly, if you really, right, so this would be the field from a point source. Similarly, like if we were to draw the vector field representation, I think many of you would not be surprised to see. I just want to make sure my colors are coordinated, right? For a negative point source would be the same logic, only the arrows would point in. And they're still getting smaller and smaller by the same amount. And you notice I'm drawing like 8 I've picked. I'm drawing just enough to make the pattern as explicit as I can, right? I mean, I could draw more, but I'm trying to pick a consistent number of arrows to make the point. These would point in because remember, the field is a prediction of the force per charge, the newtons per coulomb, waiting to be exerted always on any positive 1 coulomb of charge. I'm going to warn you again, pro tip, this is something that eluded me for like 2 semesters in college. Like I missed it. That the field, we're always predicting, or we're always depicting what would happen to a positive 1 coulomb of charge. In our mind, the test charge is always positive. The source could be either one. So therefore, negatives pull in. They pull on what would be a positive sitting there, as opposed to the positives that push out. Now, I'm going to also quickly say, in case this confused you, this is what the field is doing, right? That means if I happen to place an electron somewhere in this field, it'll experience the force as predicted by these vectors. But if it's an electron, it has a negative sign. So it will end up, so it will be forced against these vectors. The vectors are a prediction of what would happen to a positive. So if you have a negative, as it turns out, the force is negated and will push out the negative. I'm over talking. You get it. But all right. So this is the vector fields of a negative point source. Okay. What we believe in that homework that you did is that the positive charge over here made this diagram, and then the negative charge made this diagram, and then you were somewhere in the middle between the two. So you were looking at how one arrow from one of them landed on another arrow from the other one of them, right? You were adding together one arrow from one picture to another, to an arrow from this picture. But not only did you only just add two dots together, you were only the whole answer you got, I hope you understand, or the whole answer we got from that homework was all about what the arrow looks like at that one point of interest at the origin. If I had asked, okay, when you're done with the homework, now that you're done with the homework, now get the answer for a different point, for the point 1, comma 1, right? You would go through all the numbers again. You'd be better at it by that point, presumably, wouldn't maybe be as stressful, but you'd have to go through all the numbers again and adjust them all for the point 1, comma 1, and you would get a new answer, a new arrow that points in a different direction with a different size, right? So what if I wanted to stand back and look at what the picture is doing in general? Like all of the arrows you would get for every single location, there would be this whole slew of arrows. And the question is, could I infer could I zoom out and just see some kind of pattern of all the arrows so I could get a sense of what's going on in this region in the lab in general? Well, it's a heck of a lot of arrows to draw if I want to do that. Already, just for each one of these dots, I've got a lot of arrows that I had to draw just to get the pattern across. So what we do is we make this leap. We go to this new kind of representation. So I'm going to turn the page, obviously. What this my handwriting says is, so for most real situations, larger, smoother situations, we zoom out, and instead of getting focused on each individual arrow, we look at the pattern of all the arrows. In our mind, we sort of sew up, we connect all the arrows together. We say, oh, I see what's happening here. Yeah, those arrows are, on the top, they're getting smaller and smaller, but they're continuing to get smaller and smaller along that radial line that just goes up like that forever. And same thing, down here and down here. So in our minds, we stand back and we sew up all the arrows together. And we create this new kind of representation that you see all over the web that you've heard of, and you'll know what I'm talking about when you see it. We create this new way of thinking about fields called a field line diagram, or a field line representation, or in general, in other words, we've been thinking about fields as vectors. We're now, as represented by vectors, now we're going to start thinking of fields as not represented by vectors, but represented by lines. And what are the lines? Ultimately, the lines are the sewing up, the connecting of all the field vectors so that we see the pattern of vectors, the distribution of the vectors, rather than any individual vector itself. So a field line diagram for these situations looks like this. Okay, I'm good now. So this is so what I've done, just like I said, I just sewed up the arrows, all the arrows like along a given radio line. Whoa, hello. I just connected them together. Doesn't seem like that big of a deal in a way. In a way, what I'm saying is I just reduced the number of lines in my picture by a factor of three. I mean, right? It's not a huge thing yet, but this is the change I'm making even to deal with one dot. You might begin to imagine that if we start dealing with more and more dots, this improvement or this zooming out is going to make a big distinction. So I'm saying now, I took all of those outward vectors and I sewed them up together. So instead of like three smaller and smaller vectors on any given span, I now have like one long line along each span, right? And notice I I very deliberately have taken the arrowheads and shoved them to the middle of these lines. Like they're no longer tips and tails anymore. There's just lines that have particular direction. Keep that in mind. Now, as you might guess, I'll go back to that in a second, but as you might imagine correctly, if I do it to the negative, same logic. Now they go in because it's a negative, right? So what I'm trying to do here is simplify my picture, right? Of course, I'm trying to zoom out so that my picture can ultimately capture more complicated or more grand situations, more realistic situations. But of course, I'm trying to simplify maybe the approach, but I still want to preserve, to capture all the same information that I ever was concerned with. Now, there's two types of information that these pictures, that vectors are meant to convey. The whole point of any model I come up with in my mind, the whole point of any model is it's got to convey magnitude and direction. Like that's the focus here. That's what vectors were for in the first place. Can they get across the idea of size and direction? So if these diagrams, so if I simplify things so much that my life is a lot easier, but I don't still accomplish the same task, that's too simple, right? Let's make sure these diagrams are still conveying the same information. Um, I'm going to go in opposite order for reasons. Whoa, hello. Oh my God. 1 second. Sorry, I don't know why that happened. Okay, I'm over talking this as usual. Looking, okay. Is there something in the chat? Okay. The handwriting says the direction of E field at any point in space, real space, is represented by the orientation, the arrowhead of the corresponding line on the page. In other words, just what you would think. How can you tell direction from these pictures? You look at those arrowheads. Now, again, you know, and you'll see why in a moment, those arrowheads, they are arrowheads. They're not actually tips. They're not drawn at the end of a line or the beginning of a line or anything. They're just like somewhere in the line. And in fact, by the way, some websites and chat GPTs and stuff will even to really emphasize that these arrowheads are not tips. You might even see like um, websites and stuff where they have like a bunch of these arrowheads. You can do that. You can just keep you can put the arrowheads like all through the line just to emphasize like this is the direction that the line is going in. So if you want to know what the direction the field is going in a point in space, whatever point you are on the page, you look to the nearest line, and whatever that line is doing, that's what the field is doing, just as you would expect. One little technicality about that, which you'll see, is technically what you do if you're looking on the page to see what direction the field is going. You look at the nearest line, and it turns out you'll see sometimes these lines are curved, actually. So if it's curved, you imagine a tangent line to the curve at the point you're looking. And whichever way that tangent line is going is the direction of that curve. That sounds very technical, but again, it's intuitive. We're basically just saying, like, however, whichever way the line is bending at that point, that's what the field is doing. So in other words, direction seems still to be sort of preserved and still seems the same kind of concept. You know, it's arrowheads, just like before. That doesn't seem that different. But then comes the question of magnitude. So here's where I have to pause. Now, if we're talking about magnitude here, remember the whole thing that we loved about arrows, and we still love arrows, physicists. The thing we loved about arrows is that the tip shows you direction, and the size of the arrow, the length of the arrow shows you magnitude of whatever vector quantity that arrow is representing, right? That's like very convenient. What I want to emphasize now is by sewing up the arrows, we made our life easier on one hand. We zoomed out. But once we sewed up those arrows and went to this field line way of thinking, we seem to have lost something. Well, we have lost something. These lines no longer, and I want to emphasize this, these lines no longer have length in any meaningful way. I'm going to expand what I mean by meaning in a couple of minutes, but what I'm literally saying is if a line on my page seems to have a length, like I'm not saying you couldn't put a ruler to it and like say it's 6 centimeters or something, but it doesn't mean anything, the length. You're going to see in a couple of minutes that the way I draw these lines, I'm either always connecting like a positive charge to a negative charge, or like they're always like landing somewhere, and that forces their length, and it doesn't say anything, and therefore their length is forced by like another consideration, and doesn't tell you anything about their magnitude. And or one of the reasons that we put these arrowheads like sort of wherever we put them is we're trying to get across that if I don't see an obvious stopping point for one of those lines, I'm supposed to believe it's just going on forever. These, and they do. throughout space. Like if you put a proton somewhere in the universe, KQQ over R squared. I don't care how big the R is in the denominator. If the R is any number in the denominator, then the whole fraction is some kind of number, like non-zero, right? In other words, protons push everywhere in space. Their push gets weaker and weaker as you get farther away, but it's always something. So in other words, the effect, just like the sun gravitationally pulls to everywhere in space. Now, granted, if you're really, really far away from our sun, you're probably affected by it very, very little and very much more by whatever star you're near, right? So, but the idea behind gravity and electricity, that R is in the denominator. That R can be as high as it wants, and it's still going to spit out some kind of number for the whole fraction. So these lines, these field lines, I stop them as a matter of practicality. Like my pen stops because I've got a life to live, and I run out of paper and ink. But there's the idea is if you don't see an obvious stopping point or starting points, any of these lines, we're believing they're going on forever. So their length is not telling us anything. So we've lost that aspect of the vector field way of the vector way of representing fields. Like no longer can the length of a line show magnitude. So the question is, how do we read magnitude from the picture? Like I'm looking at this picture right now. I believe that if you are close to the negative q, I believe from the equation and my other knowledge that you'd be pulled pretty hard to that negative q. I believe, in other words, the field is strong near the negative q. I believe we already know that the field is weaker and weaker as you get away from the negative q. Now, again, that is conveyed in a picture like this. Like as you get farther and farther away, the arrows get shorter. You can see that in the picture. And we're not just talking rough, approximate pictures. Remember, in physics, one of the reasons we emphasize diagrams so much, step 1 DFP, is when you draw these diagrams seriously to scale. We said this the other day about the vectors you were drawing in homework. If you literally pick a scaling factor and draw these things to scale, they're not just roughly helping you visualize something. They are literally computational tools. So I'm saying if I look at this picture, if I did everything to scale, I could figure out how weak the field is way far away from negative q. I can figure out how weak the field is from how small that arrow is out there. And I could see that it's weaker than it is super close. Right? But that does not seem, at first glance, that does not seem to be conveyed by this picture or this picture. But it is. Well, wait, I'm going to look at the time. 10:07. Yeah, I think we have. I'm going to ask a hard question. So I'm going to turn it to you for a minute. It's a concept question. First of all, okay, my first question, just control because this is going to be a little tricky. It's not meant to be a trick, but so just control. First of all, who's still with me? Like, who knows that I'm about to ask a question? Raise your hand, electronic hand if you understand that I'm about to ask you. So, thank you, Nadine. Awesome. And who else? Thank you, Lunar. Thank you. You guys are great. I love this class. I'm going to miss this class after it kills me. Mark, thank you, Mark. Okay, awesome. So here comes my question. If you look at this picture or you look at this picture, and you can do this in the private chat because again, I don't think this is easy what I'm asking right now. So feel free to use the private chat. I mean, as opposed to public. I feel like there is an aspect of this picture that there is something happening in the pattern of the arrows that gets across the idea that somehow the field is stronger, nearer to the plus Q than it is farther out from the plus Q. Like there's something about this picture. Now, it's not the length of the arrows because the arrows don't have length anymore. But can you see is there any visual aspect of this picture that seems to suggest weakness perfect? Perfect. I mean, I just got one person in the chat. Oh, maybe. All right. I'm going to pause to give. Maybe there's two. Oh, there's two. Wait. Oh my God. Oh my God. There's a lot in the chat. This is awesome. Oh my God. Awesome. And I'm hearing from a bunch of different people, very different people, and some not always the same people either. That's great. All right. I'm going to read these out loud. Well, and everybody has made it clear that they understand the question. And in fact, I pretty much agree with both of these. I'm just going to read out without names. I hear distance between the arrows is decreasing, the size of the arrowhead, the gap between the arrows, spreading out, thus indicating weaker. So all sort of different words, but I think for the most part, we're all noticing. This is great. Please give yourself points for that. Seriously. I think we're all noticing, yes, I agree, that the arrows are like spreading out. They're getting farther and farther from each other, from one another in this picture and in this picture. And in fact, they're getting spread out kind of in the same way. Like if I go here, that those two arrows are much farther away from each other than they are over here, but they're farther away from each other by the same amount here as compared to there, right? There's a pattern of the spreading outness. So I'm going to put it in tech. So I agree with you. What seems to be the case is that if you want to tell how strong the field is from a picture like this, you look at how crowded the arrows are in a given region. That is exactly right. And that's awesome. And we're going to nail that down and say, I'm very impressed, honestly. Um, sorry, yeah. Okay, just to make this explicit, I'm agreeing with you guys. The answer, uh, so how an E field line diagram conveys magnitude of field is this. The magnitude of E field at some point in space is indicated or represented by the density of field lines at the corresponding point on the page. And by density, we literally mean number of lines per unit area. Like why area? Because we're on a page or a computer screen. Like these are drawings. So they're two-dimensional. Sorry. So you go to some little square centimeter on the page, and the number of lines that cut through that square centimeter indicates how strong the field is at the point in space that you're representing by that region on the page. And let me emphasize again, once we get more into this, if the field line picture is actually drawn, precisely, or generated by computer software or ChatGPT or whatever. This is not a paid advertisement. Like then there'd be some scaling factor used so that when I say denser lines mean stronger field, it's totally conceivable that if it's a good enough diagram, you literally can know how strong the field is by, like you could say, 2 lines per unit centimeter by every 2 lines per square centimeter represents 1 Newton per Coulomb of field or whatever. So okay, I'm looking at the time. Okay, so we've got this new way of drawing now where we've swapped out arrows for lines And we're preserving this so that we can zoom out basically. And we're really now looking at, so now I'm saying when I think about field, and I mean this honestly, like as a human being or whatever, when I think about, oh, the electrostatic field due to this proton, sometimes for some contexts, if I'm just really thinking about one proton or something, I will think, okay, there's arrows everywhere in space, and the arrows are all pointing away from that proton. And the farther away from the proton I am, the smaller the arrow is. Now, again, and I'm not saying I literally believe there's literally arrows in space, but I am saying that if I take those arrows seriously enough, I can not only make calculations that describe what are happening right now, but I could make predictions of what's going to happen, right? That's the point of any scientific model. We're never saying that we have the whole truth. We're never saying that what we're seeing in our mind is like literally exactly what the universe is doing. It's all metaphors. It's just really, really precise metaphor, right? I'm serious. I'm not saying I don't believe so. I take science very seriously. But the reason I can take it seriously is I don't take it literally. I take every way I'm thinking, every graph, every vector, every free body diagram, and now every field line diagram is like a mapping in my mind of what's going on in the universe. I believe the universe is deeper than my mind, but I believe if I have a good map of it, I can rely on the map to make predictions of the universe, right? Just like literal maps. You don't literally think America like literally looks like it does on the page. But you do think that what's on the page in a map of America is useful enough to help you get, or GPS, whatever, will get you around America and you won't fail, right? It's like that. So field lines now, so sometimes now when I start picturing a bunch of charge over here in the lab or whatever, I don't picture arrows coming out anymore. I picture this smooth arrangement of lines that go through space. And the tighter the lines are in some place in space, the stronger the field. That's what we start now picturing. It turns out to be much more common and useful in most circumstances than the vectors were. And each line is a connecting up of a bunch of vectors. So let me give you some examples. Or in fact, yeah, in fact, okay. So I'm going to give you some, we're going to look at some examples. It's 10:15. Yeah, we're going to look at some examples and then we're going to back up after we just look at some visual examples. Uh, we'll say something about them, and then we'll I'll lay down the actual rules for how this map works. Like how do you make a field line diagram and how do you read a field line diagram is the ultimate goal for this class, is a set of rules to that effect. But I'm going to switch screens now. Hold on a second. This one of the advantages of the modern world here. This used to be so much harder. Hold on one second. Okay. Yeah. Now, obviously, you could do this on your own. Oh, not chat, sorry. And you should do this on the following. You could and should do on your own. Okay, here we go, I think. Yes. All right. All I did, and I hope this is not a paid advertisement or anything like that. All I did was, well, you see, I just typed E-field line diagrams into Google Images, right? And you get all these options, right? And I'm just using this as some examples. Like notice, like, okay, we start. I just want to make sure that you can see. Oh, What, oh, is it? Oh, it's a little overwhelming, maybe, if that's Mohammed's face. It's a little overwhelming, but it's also, so let's go slow for a second. What just happened? Why can't I? Yeah, I want to, um, is there, wait, one sec, one sec. Oh, oh. Okay. So just to start, that's exactly what you have here, right? Is exactly what we just drew. You could draw this too. But let me start warming us up from here. Like, notice if you get the idea, like we've shoved the arrowheads into the sort of centers of the lines. We've just chosen to draw 8 lines because that seems to be enough to get the point across, to get the pattern across, right? But you're going to see when we shift to slightly more intricate diagrams that even if a diagram looks more intimidating, there's always the first step that anybody does when they make a diagram is they do choose some number, some scaling factor, like 8. Like what we're saying here is not just that we're always going to have 8 lines, period. But what we're really tacitly saying in these pictures is for every unit of source charge, I will draw 8 lines, meaning for every 1 coulomb of source charge, maybe I'm going to draw 8 lines, or perhaps for every, say I don't even have numbers, I just have like letters, as you'll see in a moment. For every Q, capital Q of of source charge, I'll draw 8 lines, meaning that if somewhere else in the picture there's a 2Q or a 3Q or something like another particle that has more magnitude of charge in it, then it's going to have more lines attached to it, right? So you start with a scaling factor, and 8, you can see 8 often is what people choose because it's like just enough to make the pattern clear. But you pick a scaling factor that it literally says for each amount of given source charge, it will produce X number of lines. You begin with that, and then things can get, oh, that is not, don't even look at that. I mean, you can look, but that's magnetic. That is not what I want. I apologize. I was taking a risk on the Google and it doesn't work like that. Hold on, hold on, hold on. Hold on, hold on. I want to get back to those choices that we had before. Oh my God, everything's a disaster. Hold on, hold on. Okay, here. Okay, so now we're going to get to something slightly more like, let's get to this. Hello. I mean, I guess this is why. Okay, yes, this thing right here. Again, this is not. This thing right here. Now, what this is starting to be the situation that you did for homework. So let's talk about it for starting to be. Now, there was a couple of differences between this and the homework. Number one, really in the homework, you'd have to tilt your head. Like you would take this entire picture and sort of tilt it on its, like you'd rotate it counterclockwise. I don't know, sort of like 25 degrees or something, because in the homework, like the negative was like, or maybe I'm saying that backwards, but it wasn't horizontal. The two charges were not along a horizontal axis in the homework, right? Okay, so that's one. So you have to tilt your head to see how this is the homework. But another big difference, which we'll get to in a minute, is in the homework, the 2-point sources were not equal magnitude, right? These are. So bear that in mind for a minute. But bearing that in mind, here you have a positive point source somewhere in the lab, and you have a negative point source somewhere else nearby in the lab. Now, what this thing is doing, I mean, this picture, which suddenly does look quite elaborate. I'm sort of like stuck with Moe's. I mean, it looks elaborate. It might even look intimidating, but it's definitely patterned, right? I mean, it's intricate, but it's not a mess. And you'll see that in every one of these field line diagrams, the more intricate the situation gets, like the more charges you have creating field, for sure, the more intricate the picture gets, to the point of perhaps maybe some of them being beautiful in some of our minds. But no matter how intricate the picture is, no matter how intimidating it might look, it's always some kind of pattern. It's always an interplay, in fact, a very specific interplay of symmetry with asymmetry, like a bunch of sameness and then interesting differences. But it's definitely a pattern, right? So this thing here, like this thing here, what I want to emphasize is this is like trying to tell you what we would have gotten if you had done that one homework problem. Well, if you'd made the homework problem slightly easier and made it so that the two source charges were the same in magnitude, but then you did all your work, you got an arrow, one arrow for, pointing out from the origin, from the point 0, 0. And then, as I said before, if you like started again and figured out what the arrow looked like a little bit over, and then you started again and did all the math and figured out the arrow a little bit over from that. And then you went up and figured out the arrow. And if you figured out the arrow for every single point, sort of in that Cartesian coordinate system, within, from 0, 0 to 10, 0 to 0, 10, et cetera, all that. If you got the arrows for every one of those points, and then you sewed, and then you stood back and looked at like, oh, I see the path, like arrows are going like this, and then they're going like this, and you sewed them all up, you would have this picture. This picture is telling you the result, the combined superposition impact of 2-point sources, but for all points, all locations in the neighborhood of those 2-point sources. Hopefully you can see what I mean when I'm trying to say this may be somewhat intricate, but this is now capturing like a bajillion versions of your one homework problem pictorially. I mean, it's not spitting out the numbers, although in theory, again, if this thing were drawn to scale, so let me back up. Say we picked a scaling factor. Maybe here the scaling factor is more like 10 rather than 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's like 16 or something rather than 8. But there's some kind of consistency here where there's 16 lines coming out of the positive. There's 16 lines coming into the negative. We'll talk more about how they're doing that in a minute. And so therefore, in a way, if you picked, so what I'm trying to say, I'm looking at the time. What I'm trying to say, let's say you pick a point right here. Can I do that in a different color? Okay, I don't want to get too bogged down. If I could easily change the color, I would. Oh. Okay. If you pick a point, like random, somewhere, that could be the origin or might not be. And again, you might call it the point P, or ChatGPT and stuff would call it the field point. You pick some point there, and and you're asked, what is the field vector there? Sorry, let me back up. Again, I'm saying for every single location in this situation, there is a field vector that you could have computed through the mechanism of the homework. Like we still believe in all that. We're just trying to do bigger picture at once. So for every single point P, there's a vector sitting there that represents the magnitude and the direction of the field due to these 2-point sources. Again, I want to, so there's a vector sitting there. There's some kind of vector sitting there, and it looks something like this. Maybe, wait, maybe I can, again, I don't want to rabbit. Yeah, no, I'm sure there's a way I can do a literal arrow, but it's probably too annoying to get involved in right now. So there's an arrow sitting at any and every given point P. And that arrow would tell you what would happen to a +1 coulomb of charge if it were sitting at the point P. And look at the way I drew the arrow. What I'm trying to say is, a +1 coulomb of test charge would get shoved if it were at that location. It would get shoved a certain amount in a certain direction. Now, the certain amount, I'm just, eyeballing it. I'm not being strict to scale, but the certain amount, I believe, would be less of an amount than if it were over here. I'll erase that. But more, well, here, okay, so I'll say, like if I were over here, I believe that the arrow that I would draw would be really big. Whereas if I were over here, I believe the arrow that I would draw would be really small. Why? Because of what you guys already told me. Like over here, the field lines are close together. They're dense. So there's strong field here. So all arrows that are that this thing all was constructed from are big arrows. Here, they're far apart, so they would be small arrows. Right now, you have to know that. Like you can't, I don't mean you can't see that. You get what I'm saying. But furthermore, what's the direction? Where did I come up with the direction of this arrow? If you really think about it, I hope you understand, and you should stop me if you don't. I'm trying to say that the arrow right there at point P would be along the tangent of that particular field line. Like this arrow here is saying, oh, sorry. This arrow here is saying that this field line goes like that. So anywhere you're on that field line, you would be, if you're nearby that field line, you'd be shoved in the direction of the field line, meaning like along the tangent to that curve. Okay. So this, I'm going to say again, I'm going to go to other pictures in a minute, but I'm going to say again, it looks like, or it certainly can look, when you look at a picture like this, what the, sorry. When you look at a picture like this, it can seem as though the picture's trying to tell you something about, it seems like the negative or the positive is like being pulled to the negative, or the positive is going to move toward the negative or something like that. I want to emphasize as best as I can that is that is not what the picture is saying. The picture is not saying anything about the interaction between the positive source and the negative source. They are both sources. They're creating a situation that we are now examining. They're held in place in labs somehow. Like they might, yes, sure, they are pulling and pushing on each other, but that's not having any consequence on our life, and it's not what we're studying. We're studying what's the combined impact of the positive and negative on any other point. So this whole thing is like a mental mapping of what would happen at any place in the neighborhood of this positive and negative. Um, so it's telling you what would be the force per charge at various locations. It certainly is true. I'll say, okay, let me give you another example. Hold on. Maybe it's right here. Maybe. No, we don't. Oh, we don't. So yeah, okay. So now let's get like to these. Yeah. And I am watching the clock. I'm supposed to. Okay, like if you look, yeah, right. So now we take the same concept. Like if you look at this one here, same thing, same concept, but it's a different picture now because now this one right here, this one right here, for heaven's sakes. Okay, come on. The one I was circling, that's much more like what you did in homework, in that, yes, it's a positive near a negative, but the positive is much stronger than the negative. So if we stick with a scaling factor, if we say for every 1 coulomb of source charge, we're going to draw 8 lines, then you see more lines came out of one of those 2 dots then came into the other dot. Like there's a scaling factor being respected here. And therefore, you can see. So, what happens is not only are the lines closer together at the positive, but the whole pattern starts shifting in some different way. Now, again, it's telling you what would happen to a third party um, positive coulomb of charge that could be somewhere in that region. The arrows tell you where it would be forced, and the density of lines tell you how hard it would be forced. That's the idea of these. And yes, they get intricate, but there, as I keep saying, there's always a pattern to the intricacy, a symmetry, an interplay of symmetry and asymmetry. And what I want to tell you in the next 6 minutes is that it's not magic. It's not black magic. It's not magic. It's not arbitrary. Just like with free body diagrams or graphs, once you actually know the rules of how these things are drawn, you can get better. You can, believe it or not, be able to draw them yourself. Not perfectly. I certainly can't draw them perfectly. But you can start picturing situations with them. And more to the point, when I tell you the rules now, with the remaining 6 minutes, what's really helpful about the rules is you'll start to be able to read and understand what these things are saying a little bit better. So we have 6 minutes for me to give you the rules. I just want to say one last thing about these pictures or show you one. Now you could just, I encourage you on your own, just type in EFieldLines into Google Images and, poke around, like just get used to them. This is one of the advantages, certainly. But why is it not? Oh, come on. If I can't do this, I won't. But so my computer's free. There's too much going on. Talk about not paid advertisements. Good heavens. All right. Okay. I'm just going to assert we have 5 minutes. There's other pictures I could show you too. Maybe I will next time. I want you to realize that once you can start creating situations from things that are not just dots. Like if you poke around more, you start seeing the E field lines from a line of charge or from a plate of charge or from a sphere of charge. And that's ultimately where our whole ship is heading, is to these continuous distributions of charge. But in order to get there, let's understand how these lines are being drawn in the first place. So we've got 5 minutes, so I'm going to switch the screen share back, or I'm going to stop the share. Okay. And back to, and again, I do know that we only have four. Okay. So I think what I'm going to, oh my God, hello. I do really want to get you these rules before the period ends. So I'm going to ask your indulgence. What I'm going to do, well, no, I'm just going to do it. I'm going to just try to not explain them. I'm just going to say them and write them so that you have them. Okay. Actually, and this is true for any field line diagrams. Okay, first, you choose a scaling factor, like I've been saying, and you stick with it. Then, and again, this will be in the PDF. Obviously, I'm going to go fast because I wanted, but of course, this will be uploaded in the PDF. 2A. Okay, I'll explain it. So then you start drawing lines. Like you look at your positive sources and you start drawing lines coming out of it. You know, if it's one cool eight, and you're going to draw them as symmetrically as you can. You'll see that in a minute. But you start them at positives, and then for any negatives you have, every line ends at a negative. If they're equal and opposite, all eight will end at a negative. If there's more positive than negative, so you draw eight coming out of the positive, but now only six of them land at negative, where do the rest of them go? They go off to infinity. So nothing ever just stops spontaneously on the page. Everything either starts at positive or comes in from infinity and ends at negative or goes into infinity. And then, believe it or not, there's very little left. Lines can bend or curve. They can, as you see, but they cannot cross. Lines never cross. Following that rule, saying, all right, I'm allowed to bend lines. I'm going to start everything at positive and end anything I can at a negative. And if I can't, it goes off to infinity. I'm allowed to bend them, but I'm not allowed to cross them. Then the final rule is group lines in as symmetric, smooth, and simple a pattern as possible, obeying the top three rules. That's it. Like literally, I'm saying you play, and I know it's 1040, but believe it or not, all you do is you look at your positives and negatives. You start all your lines at positives. You end as many as you can at negatives. Anything that is left over goes to infinity or comes from infinity. And you just do whatever you can to get all the lines to go from positive to negative, allowing them to bend. But in other words, you never do anything discontinuous. You don't make a sudden sharp turn to the left with a line. If the lines have to start changing their direction, they do it smoothly in groups. Everything is as simple and symmetric as it can possibly be, given the situation itself. And if you go back and Google images, okay, it's 1041, you'll see that each one of those diagrams gets more and more complicated, but only because the thing's causing it is getting more and more complicated. The diagram is always, as the groups of lines are always as smooth, simple, and symmetric as they can possibly be while obeying the first three rules and respecting the charge configuration. That's it. All right, it's 1040. To be continued. You'll get your exam soon. You will. You will. Oh, there's something in the chat. Sorry. You can wait. I'll hang out. Oh, have a great day. Oh. Yes, very good critique. And that's very good. And the thing about clockwise and counterclockwise is about magnetics, actually, which we'll get to next. But that's very good. Yes, that's awesome. Awesome. If you, I don't know if she's even still here, but have a good weekend. Yes.
Okay, thank you,
Oh,
Professor.
thank you. Oh, you're already here. Okay, great. Yes, awesome. Awesome. Thank you. Okay. And give yourself points. Give yourself, okay, hold on. I'm going to turn off the record. I'm still here. If there's any questions, I'm just turning off the record.